What's that?
You can start.
Alrighty. So, good morning, good afternoon to you. Welcome to the next lecture in our series. Today we're going to talk about an introduction to parallel computing. This is one of the handful of theoretical classes that are scattered throughout the semester, where we talk about the abstract concepts behind the practical things that we're applying in the hands-on classes. I don't really have an outline for today's class. I'm going to try to make it just flow. So we'll just dive right into it. Introduction to parallel computing. So the concept is very straightforward. We normally think of computing as we have a problem and we make it into a series of instructions that we hand to a processor. So step by step, we solve this problem, and the steps are executed by the processor. And this dates back to the very beginning when Turing introduced his concept of a Turing machine back in the 30s, which was an imaginary machine with an infinite tape that would have zeros and ones, and the machine would change its state based on rules in a table lookup based on whether it read a 0 or 1. So this and even the concept of an algorithm, which is what a Turing machine defines, it's just a sequence of steps. So this idea of a sequence is inherent in computing. But with parallel programming, what we're talking about is taking that problem and dividing it into several streams of sequences to execute. And this is as different as us as an individual working on something versus us as an individual coordinating a group of people to work on something. It's a very different problem. I mean, yes, it's the same task, but the problem is fundamentally different. So we're stuck with, right now, with the hardware that we have today, the von Neumann architecture, which is very simple. We just assume it, where you have a CPU, which has the control unit, the processor, that it is using a memory where it is reading and writing state, and that it has input and output that it can read and write to. Very basic concept. Now, this concept should change soon. There are several computer architectures that are actually becoming practical, which will change this. But for now, we're stuck with this, and this is what we're going to be applying and the limits of it when dealing with parallel processing. So, looking at the problem, Flynn created this taxonomy of the ways that you can actually achieve that parallel processing. And there's 4 of them. You can have a single instruction stream and a single data stream, which is non-parallel processing. And the other 3 are forms of parallel, which is a single instruction stream but multiple data streams, multiple instruction streams and a single data stream, and then finally multiple instruction streams and multiple data streams. And this is what they look like when you think about it, right? So there's an instruction pool that's going to the processing unit and a data pool that's going to the processing unit. And by the way, that as you probably learned in class, is the fundamental leap that von Neumann made, which is treat the instructions as data, treat the data as instructions. So the only thing I'll point out here is that there really is no instance of the MISD that I've come across. It just doesn't exist. But the other three do. And they're very common. So, although there are theoretically three ways to do parallel processing, really only two of them are used. And there are three basic models of doing this. There's the shared memory model, the network model, and the directed acyclical graph. Now the DAG we'll cover in the streaming lecture. So that's the one that we're not going to cover here today, but the other two we're definitely going to cover. So the shared memory model in a practical sense is that you have all these processors and they're all accessing the same physical memory. And this is what you have today in your laptop, where you have multiple processors, right? And there are machines that are built this way. However, as you can imagine, and you're dealing with two fundamental elements, state and process. So it's a lot simpler and cleaner when you're only dealing with two fundamentals, two elementals, state and process. But the one that you're going to actually use to actually scale is the distributed memory, which is that you have each CPU has its own memory and they're communicating across a network. Now, it may be that each one of those CPUs is actually a multi-core CPU, but it's fundamentally the same concept. So, although there are two basic ideas of doing this, as we talked about in our last lecture on the evolution of the technology, really this is the model that we're stuck with for practical purposes. A distributed memory model where memory is behind each CPU, which means that you're dealing with three elementals: state, process, and message. And we'll only touch on this concept of elementals here, but when we get into the streaming and the Kafka, this will be more relevant. So another fundamental concept here, and I'll pause first off and ask if there's any questions on these models that we've gone through. It's just basic ideas, very simple concepts that there's only a handful of ways that we know right now how to handle this problem. All right, pretty basic. So at the heart of it is this issue of stateless versus stateful processing. Now, stateless is trivial. A lot of your problems go away when you're dealing with statelessness. And when you're going through the functional programming part of this lecture, you'll be taught how to create stateless functions, how a pure function is stateless, and that all the side effects are kept out of it. But even when you're applying functional programming, you may still be dealing with a stateful problem, something that inherent to the problem itself is stateful. For instance, if I'm talking about the current temperature, that's stateless. I just read the thermometer. I don't care what the thermometer was before, and I don't care what the thermometer will be. It's instantaneous. I'm living in the moment. But if I want to know what the change of temperature is over the past hour, now I have a stateful problem. It is inherently stateful. I must know what the previous temperature was in order to calculate what the current temperature is. So somewhere in the system, that state has to be stored. And that's when we start having a challenge. And we'll see why. And another more practical example is when you're dealing with financial systems. You know, a trade can be thought of as a stateless, right? I buy IBM stock or I sell IBM stock, particular quantity, particular price, that's a stateless situation. But if I need to track what my position is or how much profit or loss I've made in IBM, that's a stateful problem. And I have to keep a record of all those trades over time. And to that point, you have to have some place where you're keeping state. And we call that in these slides a data store. And it doesn't matter if it's a database, if it's in memory, if it's cache, if it's on disk, if it's a distributed cache like MemSQL or a NoSQL database or even a message bus. You are always following two steps. You're either storing a key value pair or you're getting a value for a key. I mean, that's universal. That's what you have to do in order to maintain state. So the challenge is very simple to demonstrate. And here's a very simple Scala program that runs multiple threads. So I've created a class called Ticker that is created with a name or an ID, and it's runnable. So a runnable is just something that has a method called run. And what I do is I initiate an internal variable X. I initiate a random pause, which is anywhere between 0 and 1 seconds. And then I go through an infinite loop where I increment X, and then I print out my ID and the value of X, and then I go to sleep on that thread for the random pause that I set for this particular ticker. That's pretty straightforward code, right? And then I create an app where I create 5 of these threads, and I just name them A, B, C, D, and E. And for each one of them, I start a thread with that name, and I just watch them run. Right? So here's a sample output, and each time you run this, it's going to be different because of the randomness. But this is just, you know, it's 3 columns of the output in sequence where it starts running and printing out to console. The very first thing you should note is those first 5 values, A, D, E, C, B, right? So even though in the code I created them as A, B, C, D, E, as soon as they're launched as their own threads into the system, as each one of them running independently, you are no longer in control of their sequence. They're like puppies in a box. They're just going to go when they go, right? So already out of the bat, you can see this issue of parallelism, that you're no longer dealing with a sequence. And then as you see, each one of them is updating at its own rate. A is updating much faster than B, which is updating much faster than E, right? So that gets us to the fundamental challenge of parallel processing, which is do not let different processes change the same state at the same time. Now, in the example that I just showed you, that very trivial multi-threaded program, each thread had its own state. They weren't sharing state. But if they were sharing state, we would immediately start running into problems. So use the classic example of the ATM, right? I go to terminal A, I request from my central accounting, what's my balance? It tells me I have $110. I request to withdraw $100, and it debits my account $100, and now the balance is 10, and I get my cash, right? Very straightforward, what you do all the time. But let's suppose that my wife is at another ATM exactly the same time, right? So, and in the split time between the time I request, the ATM I'm at requests what the balance is, and I'm sitting there scratching my head determining how much money I want to withdraw, whether I want to withdraw 50 or 100. My wife goes to another ATM and she sees the balance is 110 and she withdraws 50, asks to withdraw 50. Now, my transaction goes through, I withdraw 100, she withdraws the 50, and now we're overdrawn by $40. Right? It's a very trivial example. And the answer there is, the most common one is to use a lock or a mutex, a mutually exclusive object, a lock. And here's how the same scenario works with that, which is that in order to do a transaction, the terminal first requests a lock on the account, which means that nobody else can change the state until I release the lock. So I can complete my transaction while terminal A may start its transaction at the during the period of mine, but actually can't not do anything until I release the lock, and then terminal B can start its process. Right then, my wife will not overdraw because she's going to know that there's only $10 in the account. Very basic idea. So I don't want to patronize anybody, but just pause and make sure we're all up to speed on this. Any questions? All right. So in a practical application of that idea, what we normally do when we're building these distributed systems is we just hand the problem off to the database. People have been building these relational databases for enterprise purposes for decades. They are exceedingly reliable. So you, as a programmer, don't have to worry about the problem. They've handled it for you, right? So if I'm doing all my gets and puts to my data store through a commercial relational database or even an open source one like MySQL, I can be certain that all of that, no matter how many processes I have hitting it, that it's going to maintain those locks for me. So in my processing, I just put the problem out of my problem and make it somebody else's problem. SAP, someone else's problem. And the reason is because these databases, these traditional databases, have ACID, which is an acronym which stands for, I never can say this word right, atomicity, consistency, isolation, and durability. 4 basic concepts that these traditional databases have, right? So the atomic part of it is that a transaction will succeed or fail completely. So a transaction is atomic. It cannot be partially divided. And then consistency means that I will the transactions will not leave me in an invalid state. So the database won't be corrupted from a transaction. And then isolation means that the transactions running in parallel is the same as them running in series, that they cannot step on each other and form this invalid state. And then finally, durability means that if the system crashes or we lose power, those valid states are recoverable. And that if, for instance, if I fail at some time during the processing, and I come back up, I'm still at a valid state. So very basic concepts that we just take for granted with using a relational database or any other data store that is ACID. So in essence, we just give the problem away to somebody else. The challenge there is that you've created a bottleneck to your architecture. You can only go as big as your database can handle. And every computer has finite resources. It has finite memory, it has finite CPU, it has finite bandwidth. So if you're relying on a traditional database, you're only going to scale to the size of one of those three that you can afford for the machine that's running that database. So you're bottlenecked on your state. Traditionally, that hasn't been a problem for most applications. But as we've seen in the evolution of big data and with the internet, and now as we go forward with the Internet of Things, it most certainly is a problem. And now it's becoming quite common that one database cannot handle the level of data that we're dealing with on a regular basis. So the next level is to do a distributed data store. So in essence, we make several of these instances. We have data stores running on multiple machines, but we make them look as if they're one machine. And then we have the processors dealing. So we're still putting off the problem on somebody else. And no SQL data stores work this way. The challenge is that once you get beyond the shared memory model, right? Notice we went from the first one is, how do I jump back all the way back? Right? If you're dealing with one database, you're dealing with this. But as soon as you move to multiple machines, you're dealing with this, right? So with the distributed databases, even though you're pretending like they're one machine, we all know they're not. And that's where you run into the problems. You cannot, a problem is a thing in itself, right? There's the law of the conservation of complexity. We call it Hearst Law. And I wish I had a slide of that. Hearst Law states that complexity can neither be created nor destroyed. It can only be displaced. So pay attention to where you're displacing it. So here I said, you can just treat all these machines as if they were one machine. I displaced the complexity. Where did it go? It went somewhere. And it's either going to go someplace where you can manage it better, or it's going to go someplace where it will be less manageable. So when you're dealing with these distributed databases, you're faced with the CAP theorem. And CAP stands for consistency, availability, and partition tolerance. So consistency, and so this is different than ACID, right? Now with these databases, you're dealing with CAP. So with consistency is every read receives the most recent write or an error, right? So all the instances have the same data at the same time. Consistent. Availability, every request receives a response that is not an error. So I can always be up. And then partition tolerance. The system continues to operate despite an arbitrary number of messages being dropped by the network between nodes. Because remember, we're dealing with not two elementals, which is state and compute. We're dealing with three: state, compute, and message. And so CAP theorem says you can pick any two in your solution. If you can solve two of them, you will not be able to solve a third one. So this is kind of like Gödel's law that we covered before, right? Or did we cover Gödel's law in the previous lecture? Gödel proved that a set of axioms could be complete or it could be consistent, but it cannot be both, right? You can either be consistent, which says that I will only prove A or not A, or I'll be complete, which means for any given A, I can prove A or not A. But if I'm complete, I will sometimes be inconsistent. But if I'm consistent, I will not be complete. So same idea here, right? And so when you're looking at all those NoSQL databases out there, or distributed data stores that are out there, you're faced with these trade-offs. And this is a perfect example of the pie metaphor, right? These different databases cropped up to solve the different spaces that exist in the challenge. So, you know, MongoDB and HBase, you know, a lot of people go, why do we have Cassandra and HBase? Don't they do the same thing? They're both based on Bigtable. Well, it's because HBase is consistent in partition tolerance, while as Cassandra is availability in partition tolerance, right? And then MySQL, which is a relational database, can run in a distributed format, but it's not partition tolerant. I'll pause there and ask if there's any questions on that. All right. So as you can see, with Cassandra, SimpleDB, and Riak and Dynamo, you're faced with, it's not consistent. So you can actually have two things changing the same state at the same time, which is the fundamental challenge we're trying to overcome. Now, I'm going to pause for a minute and talk about, just sidebar a little bit and talk about something called Zookeeper, because I don't think we have a chance to talk about it elsewhere in the series, and it's an interesting thing that keeps popping up over and over again. So when you're deploying these distributed systems, be it Kafka, Kubernetes, Hadoop, Cassandra, HBase, they all assume that you've also installed, will require that you also install Zookeeper. And one of the first things you see that's odd when you install Zookeeper is Zookeeper is a small distributed service. It runs on multiple machines. And one of the things that you see is that it has to run on an odd number of machines, which I thought was odd, right? You got to have Zookeeper running on 3 or 5 or 7 or 9 nodes, right? And it provides some very basic things, right? It's very simple, it's very fast, it's replicated, it's ordered, it has a quorum. And that's why it has to be on an odd number of machines, because it will only say a value is set if a majority of the servers have the same value, right? So in order to have a majority, you can't have a tie vote, so you have to have an odd number of Zookeeper instances. It has this concept of watches, which allows a client to be notified of a change proactively, and it's highly available, meaning that you can lose nodes and still have Zookeeper running. And the way it works is you have a set of servers here, 5. One of them will be elected as the leader, and clients can connect to any one of them and any one of the server instances to read and write from. And the last part of it is Zookeeper is just keeping a hierarchical data structure called nodes. And each node has a path. So it's just like your file structure on your desktop. And you have a very, very simple protocol that you can deal with Zookeeper. You can create a node. You can delete a node. You can ask if a node exists. You can get the data for the node. You can set the data for the node. You can get the children from a node, and then you can ask to wait to be synchronized. That's it, right? So these nodes, they have a path, they have a name, and you can put a value there. And the value that you're putting there, that data, is small, right? You're not storing gigabytes of data in here. You're storing kilobytes of data in here. It's a very lean, minimalistic data store. Now, why does this exist? Well, because everybody's trying to do the same thing with all these distributed systems, and it's very hard. Like we just assume the database can handle the stuff because there's been engineers that have worked on that for years and years and years to avoid that two things change in the same state at the same time. Rewriting that over and over and over again in these distributed systems is just silly. So they pulled it out and isolated it, and then everybody gets to reuse the same thing, right? And what are some of the use cases? If I'm building a distributed system, what would I use Zookeeper for? Well, one of them is to elect a leader. As you saw, Zookeeper elects a leader. Now, if you have multiple servers coming up and they're running as peers, right? How do you have one of the peers get to be the leader? Well, you can use Zookeeper for that, because only one of them will be able to grab the token for leader. You can use it as a name service, like domain name service. You can use it for load balancing the partition. So think of this way. If I had a node with a bunch of children, and each child represents a partition, then I can have each one of the participants in my system grab a partition. And then because I have notification, I can watch, I can get notified if one of those things, one of the partitions is released, and then we can share the partitions. So it's a simple way of all my servers sharing that state of who owns what partition. Which in essence is just a mutex. You're just sharing locks across multiple processes. You can share configuration. You can even use Zookeeper as a very simple pub sub, right? Because things can watch for the change of state or change of data on a node. If I write to a node, everything watching that node will receive the change, and vice versa. So what you have with this is, if you're trying to build a distributed system, and you need, instead of trying to recreate that highly reliable way of replicated, ordered, highly available, fast data, and that's one of the key things about Zookeeper, is it's exceedingly fast. The way that you can read to it, and get a response immediately. The way you can write to it, it can write to the other nodes and get a quorum and get back to you and say, yeah, that transaction is good, is exceedingly efficient. Much more efficient than what you're going to write yourself with the given resources. So it's not the whole thing, right? But if you're dealing with, as we were talking about, stateful and stateless, right? And how you can have stateless functions dealing with a stateful problem, and you just put the side effects to another level outside the function. Here's another example of that, where you can, instead of using a relational database, you can use something different, and then try to compartmentalize, try to keep that the smallest part of statefulness as possible, and hand it off to Zookeeper to manage. The point here is that the state's your problem, and you've got to come up with novel ways of how to contain that problem and push it to a place where it's more maintainable, not less maintainable. So for a stateful processing, you can either lock or partition, and locks are expensive. Zookeeper makes it as less expensive as possible, but it's still expensive. So that example that we had before of the two terminals requesting a lock in order to process, that's pretty straightforward when you're dealing with two terminals. But if you're dealing with thousands of nodes or hundreds of thousands of processes running in parallel, the locking becomes really expensive. And it's much better if you can just run, everybody can do their own job without having to worry about the other guy and stepping on each other's foot. And that's how you partition. So partition is very straightforward. I mean, each processor is dealing with its own subset of the data store. And you make sure that if it's partitioned properly, if it's partitioned by key, a particular value, I mean, if you're partitioned by the key will always go to the same partition. So this way, you don't have to deal with locks, because that state will only be changed by one processor, because that state will only exist in one data store, and only one processor is affecting that data store. One of the models that works in a partition way at the tiniest level is an actor model. And I'll just touch on this here to put it in context. That actor model is a form of partitioning for distributed parallel programming. But we've got a whole other lecture on the actor model in ACCA, so I won't spend a lot of time today talking about it. I'll just touch on it. So an actor is a primitive unit of computation. It's kind of like an object, right? Where an object, you're supposed to call the methods to change the state, and the actor wraps the object wraps the state behind those methods. An actor is kind of like that, but instead of calling methods, you send it asynchronous messages into its mailbox, and it responds to those messages in sequence. And it can do one of three things. It can create more actors, it can send messages to other actors, or it can designate what to do with the next message, which means change its internal state. That's the basic concept of an actor, which you've got a very tiny bit of code around a very tiny piece of state, and then there's just millions of these things. So you've got it off the thread. You're not. It can scale. You can have a handful of threads dealing with a whole bunch of actors. It's a very powerful model. But like I said, we'll talk about it more in the other. Another form of partitioning is mapping, which is the idea that, you know, we normally, when we're dealing with, when we first start programming, we do a for next loop, right? We go for I equal 1 to 10, and then you step through it. When I is 1, when I is 2, when I is 3, when I is 4. And that's the sequential processing of a map. But you can actually do it in parallel, right? You could just say, this function is going to apply for the value 1, this function is going to apply for the value 2, etc. So you just map it through. You can run the whole list simultaneously if the same function is being applied for every element in the list. Basic map. Reduction is also, we think of serialized, right? Where we say, okay, I have a list of 10 numbers and I want to add them. So I say, I have 1, and then I add 2 to it, and that gives me 3, and now I add 3 to it, and that becomes 6, et cetera, et cetera. I'm going through a reduction in a serial form, but you can actually parallelize reduction. So this is another idea of partitioned work. And then scan is also, we think of scan as a serial process, but it too, it's a bit more complicated. But a scan can also be run in a partition parallel format. And there are other patterns like this. There's fork and join, et cetera, but these are the key ones that you deal with. And that's where dealing with those things in an abstract level that people have been talking about for years, we actually deal with MapReduce, right? And we touched on this last lecture, how Google published MapReduce in 2004, and it had parallelization, distribution, and fault tolerance. And one of the key things was that you move the program to the data, not the data to the program. And we also saw this the very basic word count, where you have an input, which is a list of nouns, you split it, you count the number of instances each noun exists, you shuffle them, and you reduce based on the shuffling, and you get a final word count. It's a very boring example. So came up with a more common example, right? Which is, we have this ticker data. And what it does is, and you can download this off the internet, this data is readily available, and it gets rather large rather quickly, is you have, for each ticker symbol, we have a 5-minute gap where we have the high, the low, the opening and close price, and how many shares were sold, the volume, in that 5-minute window. And we can have this for years of data. And this itself can be quite large, but if you actually went for every trade that adds up to this 5-minute window, then you're dealing with terabytes of data, right? Or petabytes of data. So we have this, this data with 5-minute windows of pricing and volume. And what we'd like to have is the volume weighted average price for the day, VWAP. And this is a value that's often used on Wall Street, right? In essence, brokers you'll trade with a broker and say, I want to trade this stock 1 million shares for the value weighted average price for the day. And then it's up to the broker to beat that value weighted average price in his trading in order to make money. So value weighted average price is simply instead of just averaging the prices, you multiply the price times the number of shares and divide by the total number of shares in order to get the value weighted average price. There's also a time weighted average price, but we're not going to touch that. So a simple MapReduce code is here. So when you launch a MapReduce, you pretty much tell the framework, you say, here's my mapper function, here's my reducer function, and here's my data source, run, right? And you say, by the way, you have authority to run on these 50 machines, and this data stored on those 50 machines, and each machine has 16 cores, so you can have 32 threads on each machine. So that's what, 1,000 different threads running the mapper. And what may happen is I've got 1,000 slots to run that mapper, but there may be 50,000 files, right? So I'm going to run a mapper in a slot on a file, and then when it's done, I'm going to drop it, create another file, run that in that slot, and I'll just keep doing that until I've gone through all 50,000 threads have run on those 1,000 slots. And just like you saw our original threading, which is the different threads were running at different times, those slots, some slots may be going through files much faster than other slots, right? Depending on the file that they happen to get, big or small. So here, I just create a very simple thing. I create a tick object, which is a case class in Scala that just takes that line of text and turns it into a more usable object. I didn't bother writing the parse tick method, which would create a case class from that string, but it's pretty straightforward to do a split and on the string by comma and populate that. But really what I wanted to do, if you look at the map method in my VWAP mapper, it's taking the text, it gets the input of a text, and it outputs a tick date and tick, right? So to the context, which is the system, it says, okay, you gave me a key and a value, and I want to write a key and a value. So I'm writing out a tick date and a tick. So just to jump forward real quick, for the mapper, I'm getting a string, and I'm outputting two objects, a tick date and a tick object. I mean, sorry, yeah, a case classes. And then on the reducer, I'm getting the input is the tick date and a sequence of all the ticks that had the same tick date, right? That's what the reducer gets. So for a given value, for a given key, it gets all the values that had that key. And then it can do its work, which is calculate the VWAP, right? So that's what the second thing here does, is it gets a tick date, and it gets a sequence of those ticks, and then it does a simple mathematics of a fold left here, where it's just iterating over that list and doing the math of creating that value weighted average price. And then at the end, it writes out the key and that value weighted average price. That's MapReduce. Any questions on that code and how that works? I know it's going over very quickly, but it's very simple methods, right? And the really trick is if you map it, you take your input and you map it the right way, your reducer is going to get all the values for a particular key. It's guaranteed. That's how I solve the fundamental problem, which is two things aren't trying to change the same state. One reducer gets all the values for a particular key, and it's able to make its calculation and write it to the output. All right. Now, in Scala, and this is why I think it's so key that you use a functional programming language when dealing with streaming and parallel programming, is because at a line of code, you're thinking in terms of streams, right? So every list object, every sequence object, every array object in Scala has the map function built in. So on this first column, I create a list of integers, and then I can just apply a method to it. Now, under the hood, it can actually be running in parallel, making use of the resources within the CPU to apply that map function to every element in parallel to the list. And then there's it's not just simple arithmetic. There's another function here where I say if it's I want to eliminate from the list anything that's less than 2, and so it can apply that function to the list as well. And there's also reduce built-in functions. In the previous code, I showed a reduce left of how I created that VWAP. But yeah, I mean, you can reduce on a list or a sequence or an array as well. It's just built right in the code. So it's only running in one machine, mind you, but it's the same concepts at the very line of code. So you're thinking in terms of scale at the smallest level that you're working at, which is important. Any questions on that before I jump into GPUs real quick? Right. So we covered MapReduce, and then we also showed you that you can do MapReduce, the same concept of MapReduce within one single code, but this MapReduce is designed to run across thousands of machines, right? Same concepts though. The last thing I want to touch on is GPU. And unfortunately, I don't think we're going to have time in this semester to do any hands-on GPU parallel programming. But I want you to be aware of it because I believe that you will be doing GPU parallel programming in your work once you leave the school, and hopefully you'll get some hands-on while you're here. And what I'm going to talk about is the CUDA approach to GPU programming, which is from NVIDIA, which is right now the dominant one on the market. All the frameworks that you'll be dealing with on top of for machine learning run on CUDA. So what CUDA does is it has this concept of a kernel, a grid, a block, and a thread. So the kernel is how you access the GPU. It's like your port of entry. And for your particular program, you're going to have a grid. And a grid will have a series of blocks, or you can have multiple grids, right? And your grids can be 1, 2, or 3 dimensional. Your blocks can be 1, 2, or 3 dimensional. And your block is nothing but a set of threads, right? And on this thread, you're going to do very, very basic things, like arithmetic. You're going to do arithmetic, not like arithmetic. You are going to do arithmetic. That's all you're going to do. It's arithmetic on that thread. So the key here is that only at the block level can you share memory, can you share state. So you've got to be thinking, the grid cannot share, the grid is a partitioning. Well, let me say, the blocks are a partitioning at the grid level, but then within the block, the threads can share state. And the reason that it is 1, 2, or 3 dimensional is because these are graphical programming units. They're designed to mainly do 3D rendering, which has, by its name, 3 dimensions, right? You're dealing with X, Y, Z transforms of vectors, right? So they're very good at doing things, these parallel, these mapping functions. So for instance, if I had to add 2 arrays, it's trivial to do that on a GPU. And normally you're talking about an array of 1,000,000 values, right? Or millions of values. So you just need to add those. You have an array of 1,000,000 values, and you need to multiply or add it to another array of 1,000,000 values. Boom, it can be done in nanoseconds or in a GPU. And also realize, you can reduce in a, you can not only just map in a GPU, you can reduce in a GPU, and you can even scan in a GPU. So those patterns that we showed before, right? If you go back and you look at this diagram here, which was just a conceptual of how you do a parallel reduction. Well, if you look at this diagram here, this is a very practical example of how you would do a reduction in a GPU. So what you're doing is you're saying, and this is a trivial example, you wouldn't be doing it with an array of 8, you'll be doing it with an array of 8,000,000 values, right? But you would say, and those values, it may be a 2-dimensional array of values that you need to reduce, or a 3-dimensional array of values that you need to reduce. So you start with that array, and at the kernel level, you handle it off to the GPU, and you specify what block structure you want and what grid structure and block structure you want in the GPU to run on this array, which is probably maps to the shape of your array. It runs it, and then it hands back a value or an array back to your code that's running in the CPU through that kernel API. Make sense? Now, right now, to do this, you have CUDA only works with C right now, and C programming is not fun. I don't recommend it to anybody. But they are working on, you do have access to these high-level machine learning libraries that do that for you, like TensorFlow. And there's some work in allowing Scala, that you can take a block of Scala and say, I want this to run on GPU. Some people are working on that, and we as a company are looking very heavily into how do we get that mainstream. So we can take Scala program and use that power that's sitting on your desktop. Last concept, and we're going to be finishing up a little early today. There are limits to parallel programming. You cannot scale infinitely because there is an overhead to scaling. And eventually the overhead becomes too much. The overhead to the scaling outweighs the advantage you get to adding one more node. So I did have a slide here. I don't know why I removed it. Thinking about solving a puzzle, right? You have a picture puzzle with all the pieces, and you're sitting at the table and you're solving it. And then you say, you know what? I want my friend to help me. So the two of you are sitting at the table and you're putting the puzzle together. And then you say, you know what? Let's do this faster. Let's get 5 people working on it, or 6 people. Now you're starting to have some collisions because a couple of you are reaching for the same puzzle piece at the same time. Eventually, you can't have, if you get like beyond 6 people, the trouble of having that person participate becomes more than how much they increase the solving of the problem. Well, that's the same idea here. So there are limits. I'll just reference Amdahl's law and Gustafson's law for you guys to go look at if you're interested, but there are some mathematics behind this on where you can plateau, where the trade-offs are. And the last thing I want to talk about is with the parallelism and where you're storing your state, and the fact that there's only so much RAM that can go in one machine, and eventually you have to network these things. You've really got to appreciate the difference between RAM access and disk or network access. And the RAM access is counted in nanoseconds, and disk and network is in milliseconds, which means that if a read from memory took a minute, a read from the network takes 2 months, 60 days. That's the order of magnitude you're dealing with. And so that's what, when you're dealing with the parallel problem, and the parallel problem is about time, right? If we had infinite time, we could do everything in sequence. But we don't have infinite time. That's why we're running it in parallel. The difference between, I go all the way to the beginning, the difference between this is a minute and this is 60 days. So how you solve these problems, and whether you're using GPU and what part you're doing is, how you partition it and all that stuff, have significant impact in your results. So my point here is that just because there's a lot of tools out there, just because there's a lot of frameworks out there, doesn't mean you don't have engineering challenges. If you're in this space, you're pushing the envelope. You're always trying to get more done. Your data sets are getting bigger. The questions you're asking are bigger. And as a result, no matter how advanced the tools are, you've got real engineering challenges to solve because you've got real physical limits to von Neumann machines that you're given to use. So that's it for this lecture. In the future lectures, we'll be covering 3 different things that we touched on briefly here, which is directed acyclic graphs, actors, and managing distributed state. I will cover the first and the third, and one of my colleagues will cover the second one. So with that, that covers today's lecture. I'll just pause, and we got done about 15 minutes early. I'll ask if there's any questions.